is there at a spot, right? You understand? And a position sensor senses it when it's between a range, right? You understand? Okay. So that would be like me knowing that you're sitting in your seat. A position sensor would be you could get up and move around and I would still what? Know where you're at, right? So proximity sensor would be like, all I know is that you're in a seat. And if you get up out of that seat, I what? I don't know you're there. That's proximity. So we're dealing with now is position sensors. So position sensors can either be analog or they can be digital, right? So our encoders, these are digital symbols, and we position sensors. And what's our two encoders that we looked at? Two broad categories: incremental and absolute, right? Y'all know the difference between those two. I uploaded the lectures up to YouTube, but I hadn't got a chance to last week's lectures to YouTube. It took probably 6 hours to upload or more. So, you know, it takes a little while. And then I can link them into the recorded lecture section. I ain't got around there. But if you want to look at the lectures that's been uploaded to YouTube and not linked, then you can just go up there and go to YouTube and just search for Rich Raymond, right? And then, of course, you can subscribe to that, but you're going to see all the lectures. So all the lectures really relative to this class will start with AUT 232. And then I think there's 400 and something lectures over there. I need to go back and delete some of my old classes. Okay, so we were looking at, did I open it already? Yeah, I believe I did. So we're looking at potential sensors and pots, and some of y'all are working on the lab on a pot. And so we're going to move on, guys. So you'll have the option if you want to stay and work on your potentiometer lab after class. This class gets out at 12:30. I can stay over here, and you can go up and you can finish that lab up then. A to D converters. And like I said, this is basically nice to know information. The different ways we can do analog to digital converters. What you need to know is that basically what an analog to digital converter does is what? Converts an analog input to a digital number, right? You understand that? Everybody okay? So this is an 8-bit A to D converter. So we've got some of those. We got they're 80. I have to go look. 81, 88, something like that. We have some 8-bit A to D converters. And what I might do tomorrow is actually set one of these things up so you can actually see the process. So what we do is we bring an analog input in, and then what do? So this is representing the potentiometer. So we're here to use the potentiometer from an so a potentiometer definitely gives us a watt that represents position. What does the potentiometer give us that represents position? Well, we can't deal with it because my PLCs don't understand degrees. An analog sensor's got to give us, to represent whatever it represents, it's got to give us one or two things. It's got to give us a voltage or it's got to give us a current, right? You understand? And a potentiometer is going to give us a watt, a voltage. So we bring a voltage in. So this is a voltage to non-binary converter. And then first of all, we would have to come in and we'd have to figure out a watt. Partial freeze. Transfer function, right? And then once we get a transfer function, over here it would be relative to degrees. Then we could bring that in and then we could figure out what binary number would represent each one of those degrees. understand that? Makes sense. Optical encoders, we looked at absolute encoders, and we looked at counting and binary. We learned a little bit about the two counting codes. We have the binary counting code, which is a weighted code. I mean, it's not a code. We have a binary, which is a numbering system. And then we have the gray, which is a code, right? So what's the difference between a numbering system and a code? What's a code? Cool. Yeah, it represents something. And so the gray code is a high-speed code because only one bit changes per count. The binary code is weighted, so we don't have to do any conversion before it makes sense to us, right? It makes sense. So there's gray code, here's absolute encoders, and then here's incremental encoders. And this is where we left off. And we have two. We have a single channel incremental encoder, which can give us position and speed, but it don't give us what?
Count.
Incremental encoder never gives us a count. All the incremental encoders do, it gives us a series of pulses that we have to do what? Count. Okay, you understand? So we have to have external circuitry to support an incremental encoder. An absolute encoder, we basically don't need any external circuit. Right? You understand? But what happens with an absolute encoder is the more resolution we have, the more bands we have to add. So the more bands we have to add, we're going to have a sensor for every band, right? You understand that? To sense that position. But we don't have to have any external support circuitry that says, okay, I'm at this position, right? You understand? So an incremental encoder does not give us a position. It gives us a series of pulses that we count and then use that count to represent the what? The position. That makes sense. But the incremental encoder has no limits. It's got basically one band, maybe two. If it does have another band, then it's going to be nothing but one mark that indicates an index mark that we might use to set the origin. But I haven't seen anything that I know of that uses an index mark to set the origin. Usually they set the origin or electronic clear-through program. So this guy here would have two bands. This is actually solid object. You don't see many of these. So, but this would be the index node or index mark, which would give us an indication every time we make a big revolution. And we could use this to set the point of origin, right? So I can literally rotate this until this right here came true, and then that means that your actuator would be at your point of origin. Now, once I've established a point of origin, then these guys right here mean something. So we have to count. So these we have to have external circuitry outside of the encoder wheel. Now, robots use something unique in that they call them absolute encoders, but they're not. If you looked at the technical information on robot encoders, they're called battery backed up absolute encoders. So what you do when you go out and buy an encoder for a robot, it comes in an assembly, and it's got the incremental encoder and the counters inside the encoder. So the counters are inside the encoder. So when it comes out of that incremental encoder, it looks like it's an absolute encoder, but it's not. It's actually an absolute encoder. Well, what happens if your batteries fail? So I'm sorry. So if we're not going to lose the count, we have to have batteries in the robot that keeps up power on those counters so we won't lose our origin. So what happens if the batteries in the robot fail? We lose our origin. And you turn the robot off. If you don't turn the robot off, you're okay. But as soon as you turn your robot off, you lose your origin. And now none of your programs will work. And why is that? Because it doesn't have a reference. So what we do is we have marks on the robot that we move it to and line up these marks, and then we redo origin. That would be called a quick origin. Or we can buy these special jigs that you mount on the robot, and you come and touch certain spots and set what they call a factory order. So incremental encoders are really, really nice, but what nice, they're not limited. We don't have to have all these different bands out there, right? You understand that. But we're going to have to support these things with external counters, external circuitry or counters to take care of it. We have a single channel, which doesn't give us direction. So a single channel, so this is a single channel. We have no idea which direction this thing is spinning, right? You understand that. So we can spin it counterclockwise or we can spin it clockwise, and there's no way in the world we know direction. But so we could use these on a motor or an actuator that only goes in one direction. But if I'm going to use an incremental encoder on something that goes in two directions, then we'll use what we call a quadrature incremental encoder, where we have two sensors, or maybe two sensors. Let me go with first robot that the college ever bought a long time ago. In fact, this is before we actually moved over to the other building. Nancy was an instructor. This wasn't an assistant dean, so this is quite a long time ago. My office was over here. They bought a robot, and they said, called me over here and said, "Rich, we bought a robot." And see if you can figure out how to use it. That was my first experience in robots. But what it worked off of, quadrature encoders. But the way they decided to do it was a little different. Well, there it is. My computer camera hadn't been working. This will work out better anyway. So this is the first encoders that I ran into. So it focuses in. So what it is a quadrature encoder, but what they did is they cut the slots are 90 degrees off. You see that? So if it spins, and here's the two sensors. It still has the two sensors to sense each band. So it's got infrared diodes on one side that transmits light, and it's got photodiodes on the other side that detects light. So when this thing here spins, you'll notice when I spin it in one direction, this guy right here would give me a pulse. The outside band would give me the pulse first. You see what I'm talking about? And then when I spin it this direction, the inside band would give me the pulse first. So now, depending on which one occurs first, that would give me an indication of what direction. Now, this is kind of misleading because it's only got 1, 2, 3, 4, 5, 6 slots. But this guy here runs through a gearbox. And this is a gearbox that is 65.5 to 1. So when this guy right here makes one revolution, this guy right here is turned 62, 65 and a half revolutions. So what I could do is take that 6 and multiply it by that, and that's what it sees, right? You understand, as far as the motion of the robot and what counts I'm getting off. This guy out here would have to spin what? 65.5 times for this guy over here through this gearbox to spin once. What do you mean? Well, not as fast as some of the robots we got now. These guys use the chain drive, by the way. So this guy didn't use pneumatics or hydraulics. It was electrical, but to take your servo motor to the so a servo motor is a motor that provides feedback. Okay. It's a servo system. So this guy here definitely provides feedback. And by the way, we're going to run into these things for two things. Not only for position, this guy gives us three things. What's the three things it gives us? It gives us position. It gives us speed. And this guy gives us direction, right? So we can use the speed of the pulses to give us an indication of the speed of the robots moving, right? You understand, or the actuators moving. We can use it. So we'll run back into these when we get into speed. So we'll look at these encoders when we get back to speed. So we can use these for several things. So what we did on this robot is we had a little program called the Zero program, and they had limit switches mounted on the robot, and we would run it until it hit those limit switches, and when it hit that limit switches, we'd zero our count out. And that's the way we had to do it, and it was all done by software. So these were our first servo motors, or encoders. I actually ran into it. Up until then, most of the speed systems that I seen used tach generators, so it actually gave us a voltage that was proportional to speed. And these are incremental and quadrature, so these guys would have at least 2 channels, right? You understand? Might have 3 if it's got if it does an index mark, right? Sometimes I use quadrature encoders, even if the device does not run in one direction, and I think we talked about that. So if I stop the motor and it happened to stop right here, which is probably what it does. Normally, when we reference position, we don't reference to this. And why is that? Because this is over a gap, right? Normally, what we do is we reference to this edge right here on one of these. We reference it to what we call the rising edge, the falling edge of the digital pulse. Because how many rising edges do I get? I only get 1 per pulse, right? How many falling edges do I get? I only get 1 per pulse. So what would happen is we would stop that thing right here, and then it's a motor. But what could it do? I mean, it could actually try to overshoot, undershoot. So it could literally just by vibration do what? It could be sitting here just by the vibration of the system. I don't know if you've ever been in a plant before. There's a lot of vibration going on. And the motor's sitting there vibrating, right? You understand? And it could cause that thing to be going back and forth. And every time it did that, it would do what? Count. So a lot of times they'll use a quadrature encoder, and they'll reference it to one of these, like the falling edge. And they say, okay, if this is low, and this is going low, and this is low, then that would be 1 count. Go in this direction, right? You understand? But over here, when this is going low, this guy here is high, and it would indicate the what? But it's looking at both of them, right? You understand? So instead of looking at one, it's looking at both of them. You understand what I'm saying? Pretty neat. So using a quadrature encoder, even though you're only running in one direction, would eliminate a lot of that. So here's a quadrature encoder example. And of course, this would be a rotary, right? And this right here would be now, a rotary encoder, of course, is going to move in an arc. And if we're going from a linear actuator over to a rotary encoder, we'll have to go through like a rack and pinion or some gear assembly like that. Okay. Which would be real hard to do on like a printer or something like that. And I'll go down and get it. In fact, I think it's here. We have a printer that stopped working, and we took it apart so we could see all the codes without anything. And it's got a linear encoder that it uses to sense the frequency. Just about 100% of our printers that I know of, it generates characters by dots. Now, originally we had a printer we had what they call a full form printer, which actually worked like the old typewriter. You actually used a ribbon, and you had a die that was cut that had the character on it, and it would strike the ribbon and go into the paper.
What was that called?
Oh,
I thought you said it.
I call it a full form, but that's not what it's called. That type of printer. So when the printers we put on computers originally came out, that's what they used.
I never think about that.
Yeah. They have what they call a daisy wheel printer. It was really neat, had all the characters around a thing that looked like a daisy, and this thing would spin around and the head would hit it. And then the IBM Selectric it was really neat because it had a ball that had all the characters on it, and that ball would be jumping around before it struck. It was really, really, really neat. Those were the guys that they first adopted over computers. Later on, what they decided to do was to just fire individual pins into a ribbon and create characters with a series of what? Dots. And that's what we use today. So your inkjet printer, if you look at this, you got a alignment of little squirt nozzles on there, and it literally just squirts out little drops of ink and creates characters with what? With dots. Yeah. Now, normally now they're really, really close together. The first thing we had was a 7-pin printer, and it couldn't do descenders. It couldn't do lowercase y's or anything like that. So everything was shifted up. And then they came out with the 9-pin dot matrix printers, and the only thing it added was the ability to do what? It's what we call descenders, which would be lowercase y's, lowercase g's, that kind of stuff. These characters that have to go below the line. Now, good gracious, I don't know how many dots we got. Because normally what they do is they align the dots like this now. So if you ever look at your print head and look real close, you'd see that the dots are actually aligned like this. So these guys fill in the gap between what? Between here. There's a lot of timing going on to when you squirt that ink out. A laser printer scans a laser beam shooting dots across an image from it, which is pretty neat. So we have to have external circuitry on these things too. So this guy is not telling us the direction. It's giving us a signal that indicates the direction, and it's up to your external electronics to do what? To determine whether you're going clockwise or counterclockwise or left or right. So these guys are rated with the number of pulses per revolution. These guys are rated in the number of pulses per minute. Number of pulses you get per minute, or centimeters, depending on which one you get. So when you try to do your transfer function. We are looking at this. So this is how they determine direction, is they reference it to what? Well, a edge. It doesn't make any difference. It's up to the electronics. All they're doing is referencing it to an edge. All right, you understand that? That way, they have no. That means if it got a pulse out of this guy and didn't get a pulse out of this guy, it's in true motion, right? You understand? And it knows the thing was not a legal camera, right?
But it's off 90 degrees.
Got 90 degrees. Battery backed up incremental encoders, this is what we just got through talking about. These are what most of your robots use now. So inside your robot base and inside, so somewhere in the robot itself is batteries. And they have to give you access to those because batteries do what? They die. So what you need to do is, most people have a maintenance schedule where they just go out and change those batteries out. And you don't want to turn the robot off when you change the battery. Because if you turn the robot off or the controller off, you pull the batteries out, what did you just do? Now you lost your origin. You'd have to come back and the robot would be down for a while you reorigin. I think ABB. What's that? Well, it's got batteries in there.
Batteries dead, power out.
Right. You're screwed. Well, you're not really screwed. It's the robot. All you have to do with the robot. Now, what we have to understand, a lot of your controllers use solid state memory that has to have batteries. Now, that's where you get screwed. The batteries are dead in your controller, not your robot, in your controller, and you lose power. And that happened to us. We lost everything. We lost the whole operating system and everything in that robot. Except for the boot. It would still boot, but it wouldn't load the operating system.
So you had to program post.
No, well, you couldn't program it because it had no operating system. So that would be like I lost Windows on this computer right here. If I lost Windows on this computer right here, we contacted the company that sold us, and they had a copy of the operating system, and they gave it to us. So it still had the BIOS in there. It still had the basic I/O system. Computers usually boot to a type of memory called ROM, which is a non-volatile memory, and that contains the basic operating system. This is another one, guys, that you'll run into called a linear voltage differential transformer. And this works on the concept of a transformer transferring information through a coil. So we can transfer information between wires, but we can't transfer a lot of energy through the wire. So normally what happens is when you run into a transformer, you have a core. It's a piece of metal, and we have different types of cores. And then the watt. And then the windings are either around different poles on the metal, or some of them only have one core, and then they wind the primary and the secondary on top of each other. Okay. It all depends on the design. We have what we call E-cores, so what happens is that the magnetic lines of flux are moving in the metal, and then it's transferred over to the other side through metal. Okay, and that determines, we call it the coefficient of coupling between or what we call the primary and what we call the secondary. The better coefficient of coupling we get, the more energy we can transfer from one side over to the other. That makes sense? So what we're doing here is removing the core. So what I'm sensing the position of is moving the core. Now, if you wind these things, if the primary and the secondary are wound in the same direction, which is the easiest way to do it, normally it don't make any difference. If they're wound in the same direction, then the phase of the secondary would be 180 degrees out of the primary. If they're wired in opposite directions, which is harder to do, right? You understand? Because your machines want to spin in one direction, and then I'd have to do what? I'd have to spin it in the other direction to wind the secondary. Then the two would be in phase. Now, normally that makes no difference, because all we're doing is AC. So if I hook up an AC motor, it don't care about the phase, right? You understand? If I was going to fire an SCR through a transformer, then you've got to understand the phase. So pulse transformers actually put dots on the secondary that indicates the phase. Does that make sense? So what we have here is we have one secondary that's wound in the same direction. We've got one secondary that's wound in the opposite direction. So one of them, and here's the primary in the center. So what determines the coefficient of coupling is how much of that core is within that winding. Does that make sense? So right now here, so the actuator would be attached. The actuator would be attached right here. So the voltage different transformers are basically linear position sensors. So right now what would happen, and then I come in and I sum these together. Does that make sense? So what I'm doing right here, this is called V net. So if we're in the center, what happens is these two guys do what? They're 180 degrees out of phase, so what do? They cancel each other out. That makes sense? Now if it moves in this direction, then this output would be more than that output. So it would start, my net would come up and give us something like this. If I went in the other direction, then my net would come up and give us, let me get back to it, this guy right here. Oops, sorry. Depending on the position. Let's say it's over here. So notice this one gives us that one. This one would give us what? That one. Y'all understand? So by the amplitude, we not only can know the position, so the higher the amplitude would give us the position, and then would indicate the what? position. And then the phase relationship would give us the what? That makes sense. Well, this is going to take some pretty complicated electronics to figure out. What's nice about these guys is they're very, very rugged. We can seal this thing up and run it in pretty hard, harsh environments.
Have you seen one of those?
Yeah. But it's hard to tell because basically they look like a piston. I mean, they look like it. So you might have seen one before, but you don't know it. All you know, a piston.
Is the wire insulated or just on top of each other? Back up your picture. See the wires, the one in one direction and then the one in the other direction. Oh, they touch.
What do you mean touching? What we use in transformers is we use a type of wire called magnetic wire. So what we're trying to do is we're trying to get the maximum coefficient of coupling. So yes, it's insulated because if it was not insulated,
Okay, that's all I want.
but it's insulated by what? Very, very thin. Because somebody wait. Don't sleep in my class. Just stand up. I found out a long time ago that people can't sleep when they do what? Stand up. Cows can. Anybody ever been cow tipping? You have, Mel?
All I wanted to know if it was coated. I couldn't imagine it.
Look how thin that coating is.
Oh, I know what that is.
Yeah, this is magnetic wire. Yeah, you can burn this stuff off of the light. You can literally burn it off of the light. What's that? Yeah, but what we're trying to do is we're trying to get maximum coefficient of coupling. So the closer we can get these conductors together, the better we have coupling in our transformers or even our motors. So our motors run off magnetics. So if you ever looked in a motor, it's going to have magnetic wire because what we're trying to do is get the best coupling between the magnetic fields in each conductor as we possibly can. And one of the things that determines that is how close can you get these loops together. And then the next thing that determines is what do you couple it externally with. So what we do is we put nice chunks of metal. We don't use this guy right here is not going to be solid, by the way. What happens is that if we try to use a solid chunk of metal, then this big chunk of metal would act like a conductor, and it would act like a shorted conductor. So what would happen is your transformer would be it'd get very hot, for number one, and you'd get almost no energy through it. So what we do is we take this and we break this core up, and we split it into individual little plates. And we call it lamination because they're coated with a paint that electrically isolates them from each other. Well, it's not really a dielectric. It's all it is just we're insulating these conductors, these metals from each other. So all the little currents that are introduced inside these guys don't do what? Don't add with all these together. By the way, these little currents that we don't want are called eddy currents. So the eddy currents induced into one does not add with the other. So if we look at a transformer, and a lot of times they'll seal the transformer up. If we look at a transformer, anything that deals with a varying magnetic field, we'll see that it deals with lamination. So this is a rotor off an induction motor, and you can actually see the laminations on this real well. We can look at it and see it in transformers. If they're not all sealed up real nice, I'm gonna pick it up on the camera. I don't think the camera is going to pick up the laminations. Put this against something so it don't roll off. Yeah, we can see them. Can you see them? So this core is divided up into hundreds of individual plates, and they're electrically isolated from each other. So what this does is this don't act like a conductor. It acts like, well, it's not a conductor of electricity. It acts as a conductor of a magnetic field, right? You understand? So anytime you see where something's going to have to be changing like this, right? You understand that works off induction, then you'll see laminations instead of solid chunks of metal. So these are the actual conductors right here that we're inducing the current into. These guys right here are just in there to concentrate the magnetic field that's being induced into the water. The conductors. That makes sense? No. So this is a rotor off an induction motor, and what's nice about that is you can really see laminations. But if we looked at a transformer, if you looked at the transformers up here, I think you can see the laminations on those transformers. If you look at any of these AC relays, the actual armature that moves up and down is going to be what? Laminated. Everything in there is going to be laminated, so those eddy currents don't combine and create a lot of heat and make it very inefficient.
Like thin paint or something?
Yeah, that's why it's called laminated. Lamination is what they call it because it's laminated, which means it's coated. A lot of people call this laminated wire, which is basically it's just painted with a really thin paint that acts like an insulator. It has very good insulating characteristics. It's a good insulator, but the problem is that it can burn off real easy. So we have a lot of times in transformers where they get way too hot and it burns a little thing and it burns two together. Now you shorted stuff out, and as soon as you short out one of your windings, then the transformer don't give you what it's supposed to give. So every winding you short acts like one winding, and you lose one of your windings in your ratio, right? You understand? And usually it just cascades after that. You get cascades. So now the transformer pulls more current, which means it gets hotter, which burns off more lamination. So that's usually what happens with these, is that even in motors. So you can see a motor. I think I got a picture some way. A motor that's got way too hot, the lamination will turn black, and you got a big problem after that. Yeah. Well, see, and it's basically charged the lamination, and now you got windings that's shorted, and that's going to cause a big problem. So yeah, they're isolated from each other. This shows it as being orange. It kind of looks like copper, but it's not. They're all laminated. So we got to have a special circuitry that takes the output of the LVDT and it comes over and does what? Gives us a count and gives us some direction of which way it's going. Are we okay? This is a linear optical encoder. This should have been back on the slide. Should have been over on the other side. Okay, guys, y'all take a 2-minute break. Everybody okay so far? Yeah, that's amazing. So position, weight, speed, count, pressure, flow. We're going to look at our light sensors right now. Thickness, time, gases, liquids, motion, orientation, shape, size, proximity, moisture, or viscosity. These are different types of light sensors. Photoresistive, and what's going to happen is we're going to combine these. One of our primary uses of light is in proximity. We can use some of the characteristics of light to sense when something's at a position, right? Like my encoder that I passed on. So that thing is either doing like blocking light or letting the light pass from the transmitter to the receiver. Photoresistors, photodiodes, phototransistors, and photovoltaic cells. Most people call solar cells. So these are photoresistors. And they're called photoresistors because why? They vary their resistance to light. And I hope I remember to bring those over here. I usually carry this like this. There's my EG stick. I know magnets. And I don't see my case in here that's got photoresist in it. I did everything else with that. So somehow my case got pulled out, and I'll try to remember to find them and pick them back up. These are pretty important. You'll run into these all over the place. So this uses a characteristics that's common to solid semiconductors, where they actually change their resistance relative to light. Semiconductor light controlled variable resistor ohms decrease as light intensity increases. Using light sensitive detection circuits, using light and dark activated switch circuits. So we run these all the time. We used to for these things and other methods of switching AC using solid state instead of using relays. Used to all your lights were on timers. All these parking lot lights and everything was on a timer. And so what they had to do was basically adjust them all the time because our length of time during the day. And you can still see every once in a while these parking lots on a timer because you'll go out there in the summer and the parking lot lights will be on at 5 o'clock because they've got to still set for winter, right? You understand? Now just about all your street lights use these guys as a sensor to sense when it's what? Dark or light. I got motion detectors on my house. But they don't come on during the day. Because what? I got one of these in there, right? That's sensing when it's what? Night or day. So these guys, and that's what I wanted to show y'all, they're really, really neat. I was going to put an ohm meter across them, that you actually see when I put my hand on it, the resistance would go up, and I take my hand off, the resistance would go down. So these guys are fairly sensitive. You can get them in different ohm ranges. Now, of course, we can't see in ohms, right? You understand that? So we would have to run this either through a Wheatstone bridge or through a voltage divider, have it a part of a voltage divider to generate a voltage for these sensors. So these guys can't turn on the street light, but they could do what? They could sense when the electronics turn it on, right? Does that make sense?
Well, that's the dawn light.
They have these in there.
Light.
Yeah, it has, but these things are pretty cheap. We have other methods we can sense light, but these guys sense a wide range of colors. So we'll use these, especially white light. These works real well with white light.
Most detectors are really sensing light.
No, they use two sensors. They have a motion detector, and then they also have this guy. So I can walk in front of my motion detector all day during the day and do this, and they won't come on. But when it gets dark, and I go out there and do this, they come on. So it's got two sensors. It's got a sensor that senses motion, and then it's got one of these that senses day and night, right? So, yeah.
Yeah, I got one in my truck that dims the speed on and stuff.
Yeah, a lot of cars have automatic dimmers on them, so you run your lights on bright, and then when another car light shines on you, it automatically dims.
That's the same thing as like in your phone.
Huh?
That's like the same thing that's in your phone.
Yeah, your phone probably has a little more complicated, but it's got a light sensor.
Yeah.
A lot of digital cameras have light sensors on there, and they'll judge how much of a flash to put out depending on how dark it is. So the lighter you are, your light. A lot of times that's that might be done by time, but it's also going to be done by one of these guys. So you walk in a phone, you have it to auto dark on you, and when it gets dark, it actually lowers the intensity on the display. And of course, the thing that eats up the most power on your cell phone is what? Your display, the brightness or your display. That's the guy. So you can talk on it all day long, usually. But if you use that display a lot, it's going to do what? It's going to go down. This is the ISO, the International Standard symbol for resistors. So what we do is normally, and a lot of times they'll leave off the circle. It's very common, but they'll always put the arrows pointing in. This means it's sensitive. And these are light sensitive. This is the ISO symbol for a resistor. A lot of people like this guy right here is hard to draw. Well, it's not hard to draw. Just a lot of people draw it. It looks like a transformer, but they lived it. So this is the international symbol for a transformer. I'm sorry, for a transformer for a resistor. Okay. So you're gonna run into these guys all over the place. All over the place. And if they're easy to hook up, you can get them different sizes, different lumens, and all kinds of stuff that they pick up. But everyone I've ever seen, the resistance goes down with light. The resistance goes up the more it moves to dark. But there's no such thing as zero resistance, right? Don't understand that. So we might run these through a Wheatstone bridge, so we can set a zero light, or zero light, right? We might run it through a comparator circuit, so we can adjust when it cuts on at night and cuts on at day. Don't understand comparators, we looked at those a little bit. They're not very complicated. Well, they are complicated circuits, but to us they're not. Most of them come in little, if they're not integrated into the electronics altogether, they come in a little 8-pin dip. We call them dips. Anybody know what dip stands for? Nobody knows what dip stands for. Dual inline package. And what I was talking about is these pins right here. So there's 8 of them, and there's 2 rows, and they're in line with each other. And each one of those has a function. Some of them are for power, and some of them would be in for one reference. So what we do is we'd come up here and we could set up a reference voltage and bring it into one of our inputs. And then we could bring in the output of our light sensor from another, bring it into the other input. And we'd pick it off right here, right, or vice versa. And it would come over here to the other input, and then these guys here would be powered. So you'd have to have power applied to your sensor. And now, or if we made this like this one, right here, and what happens is it switches condition. So if this input is bigger than that one, then the output would either be a negative voltage or it would be a 0 volts. And as soon as the positive becomes bigger than this one, it would do what? It would switch. Sometimes they power them up on plus and minus supply, and if the inverting input is greater, it'll saturate negative. If the non-inverting input is greater, it'll saturate positive. If they come up here and reference it to common, then if the non-inverting, so this guy is not called the minus input, it's called non-inverted. I'm sorry, inverted. So this guy, the output moves in the same direction. This guy, it moves in the opposite direction. Does that make sense? So if the comparator is referenced to common, circuit common, then if the if the inverting is greater, it'll go to 0. If the non-inverted is greater, it'll go to it'll saturate to whatever voltage you put up here. So I could put any voltage like 20. Well, it depends on you'd have to look at the comparator and see what the maximum differential voltage between this guy and this guy is. Well, that's why in electronics you got to be careful with these plus and minus symbols, because these are symbols. And what is a symbol? Representation. So on these guys, this is called a non-inverted input. This is called the inverted input. That makes sense? So if this one is greater, it's going to saturate this way. If this one's greater, it's going to saturate in the plus direction. And these are called comparators, the digital comparators. So what they'll do, even though the output of this is an analog, if the output of this is an analog, then this is gonna take it and convert it into a single bit digital output. So a lot of our sensors that we run into, guys, are the actual sensing element is analog. But when we see it, we get what? We get digital. And some of them will make this guy right here, variable. If this guy is variable, then what can we do? We can change where it switches at. So what we're doing is changing our reference voltage. That's applied right there. I didn't put that up there. VREF. This is a photodiode. Now the problem with the photoresistor, and we got these guys too. I'm sorry, my little package is not in my thing. I grabbed that thing up and it's supposed to have all my sensors in there. But the problem with the photoresistor is it's got a slow response time to light, so it's not instantaneous. So what that means is it works okay for a light of day sensor because the light does what? It varies real slow. So these guys here work great on that. We probably wouldn't use these on an electronic flash on a camera where it's trying to measure the amount of flash it puts out because your flash is just what? It's just there. Okay. So that means we had to come up with something that was extremely fast. So when I come up here and hit this thing, what I'm doing, guys, is I'm sending a series of pulses out this thing right here. I'm not sending one pulse, I'm sending a series of pulses, and those series of pulses change depending on which button I'm pressing here. So this is the light source right here. It's infrared, so we can't see it. Some cameras can pick it up. I don't know if this camera on this guy can pick it up or not. We had a other camera. It was a Sony camera. It was real neat that I could do that. I'm trying to get it up here so my light don't pick it up over there. Yeah, this is this one, but that would be dangerous to use because my thing up there would pick it up. This guy might pick it up. I don't know. Let's see. See it? Yeah, by my count, it did pick it up. So a lot of your cameras now automatically adjust the light. But if I point it to you, turn it back on. You don't see that, but those it's doing like that, and so a photoresistor couldn't do what? Couldn't keep up with it. It could pick it up, but by the time it responded, I would get another pulse.
You know, your cell phone camera.
Sometimes it'll pick it up.
It has, when you take pictures, the flash is on, but sometimes it doesn't. It hesitates a little bit before it flashes.
What it tries to do there is tries to fake the people out to prevent from getting. And they pick that little technique up. So you say 1, 2, 3, and everybody goes. I got pictures. I got 100 pictures of my wife. So she's one of those. Well, a lot of times they'll delay that flash just a little bit, delay the picture of just a little bit, and people will do this, and by the time it flashes, they watch. And then red eye.
Well, it might have had something to do with ambient available light compared to what flash intensity.
And the flash intensity in our cameras now are extremely smart, but it's got to be able to sense that light intensity instantly, right? Between when you click that and that flash goes out, and you'll see the duration of the flash actually varies sometimes depending on that. Photography used to be very complicated because I did it for a while, but now it's not near as complicated because basically your camera does just about everything for you. You know, it senses the light and sets the shutter speed. So the darker the light is, and you have your flash turned off, it leaves the shutter open a little while longer. It does that automatically for you now. Did it come back up there, guys? So a photodiode this would be the actual symbol. So we come over here. This is a symbol for a diode. And then what we would do is we'd come over here, and it might be in a circle. I'm not going to put it on there. And it would come in and have what? Instead of the arrows pointing in, they're going to do what? I mean, instead of the arrows pointing out, they're pointing what? In. And this is a symbol for a photodiode. Now, diode is a unique. Anybody understand check valves? What does a check valve do? It only lets something flow in one direction. So if you don't have one on your house, you need to put one on your house. Because what will happen is, if the water, if you ever get a water main break or something like that, all the water in your house is going to do what? It's going to drain out. Then when you turn it back on, they're going to fill you up your pipes again. And what do? You share the same water twice. So you can buy check valves on there. So when the water comes in this direction, it opens up and lets the water flow through. But if the water tried to go in this direction, it would do what? In fact, in fluid power, the symbol for a check valve is a ball. And then it's got a seat like that. And it's like that. So if the fluid flows in this direction, what's the ball going to do? It's going to float up, right, and let it flow through. And if it tries to come the other direction, it's going to close it off. Well, what we're doing with a diode is we're controlling the flow of electrical current. It's the check valve for current. That's what a diode is. So what we do to make the diode actually conduct is we would come over here and let's put a resistor right there. And what we would do on our DC battery, if I did DC, if I pointed the negative toward this guy right here that we call the cathode, and then I pointed the positive toward this guy, which is referred to as the anode, then it would let it conduct. It would conduct. Current would flow. It would flow in this direction right here, against the arrow. Now, it's solid state, so it's going to drop a little voltage. These guys here drop about 7/10 of a volt. Some books teach 16, some teach 17. And so if this was 24 volts, then we would measure 23.3 volts right there, which basically is everything, right? Understand? So you have a little drop. All solid state devices, these guys can act like a switch, but they will always drop a voltage, always. So they are not switches, they're solid state. Now if I was to come over here and flip this battery around, which means now I'm going to point the positive toward the cathode, and I'm going to point the negative toward the anode, and this guy right here cuts off. So we would measure 24 volts across the diode, and we'd measure 0 volts across the load, because it's an open element in the series circuit. Okay. Now the problem is that there is a path through the diode. The diode is solid state. So even though it's electronically switching it, there is a path that current can get through. We call it leakage current, and it's going to be very, very low. You wouldn't probably be able to measure it. So if you put your amp meter in the back of that thing, you reverse bias it, you would not measure the leakage current. So if we reverse bias it, is our current flow through a solid state device? Yes, it is. So when we set up when we put polarities on a solid state device to make it conduct, we call that forward bias. When we put a polarity on the device to cause it not to conduct, then we call that reverse bias. So what is bias? Bias is a DC voltage that we apply to a solid state device that controls how it works, when it conducts and when it don't conduct. So all solid state devices have to be what? Biased. So basically that's what we use resistors for. So most people don't know why we use resistors in electronics. So back in DC, you just set up these little series circuits. Now, what did those guys do? What work did they do? What type of work did those resistors do in DC? No, what type of work? They generated what? Heat. That's all they did. That's all the work they did. I mean, when you calculated watts, that was nothing but heat watts, right? Okay. But what you find out in electronics, we use resistors to bias our solid state devices to determine how they operate. So you won't ever run into a solid state circuit that won't have a bunch of resistors in there. So if you do take solid state, which is required in the ILT, then you'll learn a lot about why we actually use what we use resistors for, besides to generate water. Now that's nice. You can go out and buy an electric heater, right? You understand? You might have an electric water heater at your house, and that's basically all we're using. That's all it's using those resistors for is what? Generate water. Heat. But you snap off your microwave oven, look at that electronic control circuit on there, you're going to see a lot of resistors on there, and those guys are not in there to generate heat. They're in there to bias those solid state devices to set the operating parameters, right, of the device. So what we do with a photodiode, it's kind of weird, is we put it in the circuit reverse bias. So what I would do is I would come over here, and of course, if we was going to sense its current, we'd probably have to put it in series of a resistor. So, and then we would come in and put it in the circuit reverse bias. So it means I would come over here and I would point the negative toward the anode and the positive toward the cathode. And what the light does, it controls that leakage current. So the more light you have, the more current that flows through it backwards. It's still pretty small, right? You understand that? And the less light you have, the less leakage current you have. But what that would do is it would cause the voltage drop across that guy to change. And this guy is instantaneous. We don't understand how fast this sucker switches. So I guarantee you, up there, it's either got a photodiode or it's got a phototransistor up there. It's probably a phototransistor. We'll look at that. Okay, so notice to forward bias it, we have to point the negative. Now we're not putting a negative polarity on there. To forward bias a diode, we have to point the negative toward the cathode and we have to point the positive toward the anode. This situation right here would do what? This would forward bias. And here the photodiode would work like a diode. It would just drop about 0.7 of a volt and that'd be it. Right? You understand that? But what we do to make it act like to actually absorb that light and change the leakage current is we operate at reverse bias. So to operate at reverse bias, we do what? We put the negative toward the anode and we put the positive toward the cathode. Oops. We put the negative toward the anode and the positive toward the cathode. Y'all didn't call me out on that. But what you're going to see right off the bat is we've got to expose the silicon wafer to light. So these guys are going to have a lens on them, right? You understand that? They got a lens on them. You can get through. You can get light through them. This would let us focus the light on that encoder that I've got around. Those use photodiodes. You can tell they're photodiodes because they've only got. Oh, here we go. They're using photodiodes, and you can tell they're photodiodes because they've only got two lenses to them. These are going to pick up light over a viewable angle. The one that I have a picture for, this one is going to pick up the light when it's pointed at it because it's got a shield that comes on the outside, right? Does that make sense? So these are the photodiodes on this side, and they're the clear lens devices. They've only got two wires coming out of them, so I know they're photodiodes and not phototransistors. Phototransistors will have 3 leads coming out of them, but they look very similar. Y'all see what I'm talking about? Yes or no? Or y'all want to see it again? So these are the infrared lights right here. So you can't see these, right? You understand, unless you got something that picks them up. It's just like, you can't see this, and you can't see the remote on your TV, right? But if I point it at a camera that might have that ability, you can actually see the infrared. So this camera can actually pick up that spectrum and make it so we can do what? We can see. What I did that time was used a button that Yeah, I told it to mute it, so that guy's got a microphone on it. So these guys would have a better angle, but what they've done is they've blocked it off with actual metal brace that they're mounted on. So what these are infrared lights. So we couldn't see them, but as this moves, it breaks every one of these would break the light between the transmitter and the photodiode, between the photo LED and the photodiode, right? Or the LED and the diode. And what does LED stand for? I didn't mean no. So these are infrared LEDs right here, which means they're in a spectrum that our eyes can't see, but they're there. And what this does, it either lets the light pass through, or it lets it go through. And it looks like this has a very poor resolution, but the actual actuator would see this as 1/65th of the size, right? You understand? So it sees it as a little old tiny thing because it goes through the gear. So the actuator is actually out here after it goes up back to this 65.5 gear reduction. So so what are we doing here is if we drop the speed down, what do we increase? Torque. Yeah. So we're getting the same amount of work, right? You understand that? So this guy here would be a torque multiplier, and it's going to be a speed divider. So this guy over here is spinning like crazy. This guy over here is not moving near as much, right? And then we go through another gear reduction. We go from here to a bigger sprocket on the actual actuator itself. So to actually figure out what it meant from here to here, we would have to know the division ratio between this sprocket and the sprocket that was actually mounted to the joint, right, on the robot. And we don't have the robot anymore. So I took all these off because it was really neat to see it. So I want to see it again. Because it's hard to see the actual sensors on the encoder. So what we're going to find out, a lot of our sensors, we have to use other sensors to cause that sensor to work, right? You understand? So here we're using this is the sensing element right there. But this guy means nothing unless I can take this and convert it over to a series of pulses. So here we're using a light sensor, and we're using this as the actual sensing element. Does that make sense? This would be an incremental encoder. So this is a phototransistor. The symbol for a phototransistor, and I don't think I've seen any PNPs. So we come over here and we would do this. And we call this an NPN transistor. And what we do is we look at this arrow right here. And we got two types. We have what we call an NPN and a PNP. And what we look at this one is pointing in. This is what? Not pointing in. So this would be an NPN. This is pointing in. So this would be a what? A PNP. Huh? It does. What determines how it operates is this determines how we bias it. So to bias this guy, we would have to make this guy called emitter more negative than this guy called base. So this is the input. Now this one, we have to put the emitter would have to be positive in respect to the base. So what we do is we apply our light right here. So this is a current valve, guys. Well, what do we do with valves? What do we do with valves? We control the flow of valves, water valves. we control the flow of fluid. Water valves, we can control the flow of water, right? And y'all run into water valves all the time. We can operate them as on-off, like if I go out to the water fountain, odds are when I press the button, it's going to turn on and turn it off, right? You understand? Or we can operate it as like I got a knob on it and do what? I can actually control the flow, right? You understand? And that's what the base does. So what we're doing, if this was electrons, then this is the valve right here. It goes between two leads. This is called the emitter. And you don't have to, I'm just doing this. This is not something you need to know for this class. This is called the collector, and this is called the base. The base is the handle on your valve. So what do you do with that handle on your faucet? What do you do with that handle? To control the what? Flow. You can precisely control the flow. Well, that's exact, but you're using a mechanical advantage. Turn that sink wide open and try to stop that thing with your hand. Try to put it under your faucet. You're going to end up, you're going to be soaking wet. You cannot stop the flow of that water with your hand.
I've tried.
We do it too sometimes when we're real hot and we want to spray it on us, right? You understand? So we can't stop the flow of that water with our hand. Everybody understand that? So what we do here, we get an electrical advantage. So I put a little bit of current in here to get a lot of current right there. So I use a very little input current on the base to control what? A lot of current between the base and between the collector and the emitter. So the collector and emitter is the valve. The base is used to what? Control the valve. We can control the flow. We can make it act like a switch. We call it, we can switch it between what we call saturation and cutoff. So if I put enough base current in there, then my transistor drops almost no voltage between the base and the emitter. And if I put no base current in, the transistor switches off. So we use these as digital switches. So I can either turn them on or off, or I can control the flow of the base current, and I can control the flow between the emitter and the base. The emitter and the base. Well, these guys are really neat. So what I can do is if I can bring my light in here and get a very, very, very tiny base current but the light is controlled with light, right? You understand? Then what we have now is we got a sensor that can work faster. But what's nice about this is we can also bring this out and we can externally bias it. And which means we can set the characteristics of the sensor. So these guys are really neat. So odds are this guy right here is using a photo transistor. It's not using a photodiode. We don't operate this thing in reverse bias. All we're getting out of a photodiode is what we call leakage current. Does that sound like a lot? That's like you got a slow leak in your tire. So my wife's got a slow leak in one of her tires. We can't find it. So I have to come back every once in a while and put air in. So a photodiode is like a slow leak. We can control very little current out of a photodiode, but we can get a lot of current out of a phototransistor. Because what we're doing is we're getting this current gain between the base and over here. So phototransistors are used most often if I need a lot of current. Photodiodes, we'll have to gain those with some type of amplification or something before we can use them. But we can literally use this for something. These are phototransistors. You can identify a phototransistor. They look very similar. They're going to have a lead, right? You understand? But instead of having two leads, they're going to have what? Three. The center lead might, this little tab, this identifies the emitter. This would be the collector, and then the one on the center would be the base. But you can't, they come in all different packages, so you can't really use this package as an example. So phototransistors, the advantage of phototransistors, they're extremely fast, but we can get a lot more current out of them than out of a photodiode. All we get out of a photodiode, guys, is something we call leakage current, or leakage current change. Normally, it's in the range of nanoamps. So you can't get much work out of nanoamps. This guy depends on the size of the transistor, but milliamps, very easy to get milliamps. We get amps out of these, but Not out of photodiodes, regular transistors.
The little robots were still. Is that what they had on the front of it?
No, those are photodiodes because they only had 2 wires coming out of it. Now the photo, that's not true. So you were right. So those were not photodiodes; those were light emitting diodes. So across the front of our robot was light emitting diodes, but that thing that stood up in the center had 3 leads coming out of it. That was a phototransistor. So you're right. I got off track. So the thing's transmitting light. So we got a robot. I didn't bring one over. I can get that. That's an avoidance robot. And what it's doing is it's pulsing the light out of a photodiode. Out of an LED. And then it looks for reflection to come back off a surface. And depending on which angle it comes off, would tell the controller which way to do what. Turn the robot. I'll bring one of those over here too. I need to make a note. So what do I need so far? I need a photoresistor. I need to find my kit. I don't have it. So I got a box like this that I'm supposed to have in here. That's got photodiodes. It's got I don't have any phototransistors. I got photodiodes. I got photoresistors. I got LEDs. I got thermistors in there. So I got a bunch of stuff. I need to find that box. And I do have some phototransistors over there, by the way. So just about all our sensors now, like on this, odds are if you got a motion detector on your house, it's going to use a photoresistor. Anything where the light does not vary real fast will probably use a photoresistor. These guys are really, really cheap, right? Anything that's going to require a fast response time for a light sensor is either going to use a photodiode or a phototransistor. The advantage of a phototransistor is we can use a very small current being generated by the light over here on the base to control a pretty good, a relatively higher collective emitter. So I guarantee you this uses a phototransistor. The remote on your TV uses the what? Phototransistor as the receiver. You're right, your transmitter is infrared. Right. Why we make it infrared, of course, is there's not a lot of infrared in the white light spectrum. And then plus, it won't be annoying when it flashes. When these things first came out, the first remotes was really neat, is they generated a ding. I don't know if y'all remember those. So you hit a little button, it had a little snap on it, and it go ding, and it had a little tuning fork in there. And depending on what you clicked, it would do what? It would generate a different tone, and you had a microphone on your TV. The first one that my uncle had, he was the one that had the first color TV, and he's the first one that had the remote for the TV. And then after that, the light was actually white, but then that was very annoying, right, when you flash it. So that it didn't take them long to go to infrared. This is a photovoltaic cell, which I don't have over here. My kid over there. Most people call these solar cells. What is a solar cell?
Collect energy, like the sun or any light.
But it converts. It's a transducer, definitely. So what does it do? It takes solar energy and generates it into a electrical energy. Right?
Well, it doesn't have to be directly in the sun. It could be the light.
Well, yeah, but the brighter the light, and it should be obvious, is the brighter the light, the more energy you're going to respond. So a lot of these solar energy farms, they have auto tracking systems that do what? Yeah, they automatically change the angle to try to get as much direct light exposure as you can.
I think I got 1 or 2 of those in some yard lights, that run off the solar.
Yeah, a lot of calculators have gone to this. A lot of things. There's a lot of devices that's gone to solar energy.
I'm talking about the lights you stick up in the road.
Yeah, those. Yeah, what those do is very, very popular on these guys is to store. So they'll store them. By the way, you get DC out of these things. So what can we do with DC? Well, we can store it in batteries. Right? So a lot of times they'll store it in batteries and then use it at night. Where most of the so you're actually running out batteries at night. You just charge them during the morning.
I threw a bunch of these things away before I realized
They're
they
very
had a
expensive.
replaceable battery.
Oh yeah, I had one on my system go out. I just popped it out and carried it over to Batteries Plus, and they said, "Oh, we got that." Popped a new one in there,
Yeah, but you knew that, didn't you?
and I'm ready to rock. So yeah, mine went out too. You see these out on the interstate all the time in a rural area where you have lit signs. You'll look on the side and you'll see a solar panel pointing up at the sun, right? You understand? And charging batteries, and then at night, what do? They run them off of batteries. They have a competition every year where people build cars that run off this solar energy, and they'll have all kind of things. They've got I don't know how long it laundered up there, but they built basically a big glider. I don't forget how big the wingspan was that actually flew above the clouds, and it used solar energy to turn the propeller. What's nice here is the amount of energy you get off of this thing. These guys are nice and linear. The amount of energy you get off is directly proportional to the amount of light you're supposed to. And these things these guys are self-powered. Which means all the sensors that we've talked about so far, I have to run power to the sensor, right? These guys are self-powered. Which means we don't have to do what? We don't have to power these things up. And then we can use the amount of voltage that we get off of them to do what? Get an indication of how much light they're exposed to. Which is pretty good. But most of us just use it. You can buy these things to charge the batteries in your cell phone. It takes them a little while, but you have a lot of people that go camping and stuff, they'll buy these and they'll set them up. I think Harbor Freight sells a panel that comes with almost everything except the battery. How much are they selling it for? But it comes with the inverter. And they usually sell it in their magazine. They send me I buy stuff over there. I don't know if y'all think about Harbor Freight. They send you a catalog over time, and it's always the same thing. Well, so there's a solar panel kit. So they sell the solar panel kit for $200, but don't come with any batteries. $200. These things come down quite a bit too. I think California just passed a law where every new house being built has that solar panel. So many watts of solar panels. You could use it to charge batteries during the day, and then you could use it to do certain things at night. What the wattage rating on it is 100 watt solar panel. Now it's kind of 100, so it will provide 100 watts into something. Then your batteries are rated in watt. What are normally batteries rated in? As far as what they can, you have rated in volts, yeah, but after that, what are they rated? No, I've never seen a battery rated in watts. Y'all don't know what batteries?
Oh, amps,
No.
amps.
Well, but it's not amps. It's ampere hours. So it says that it could put out that many amps. So it's a 6 ampere hours. That means you could put 6 amps out for an hour. And then you could say it could put out 12 amps in a watt, half hour. Or you could put out, right? Or you could run, if you got 3 amps, you could run it for 2 hours, right, before it discharges. So batteries are rated in a discharge. They're rated in the voltage, but they're also rated in a discharge rate. They call them ampere hours.
I think people in campgrounds, campers, and even campers drag those things out.
Yeah, I mean you can't blame them. See, that'll run a generator. Normally, you don't need your generator. They run those at night. Well, what they can do here is do what? Put this sucker out and charge batteries up during the day, and then they got lighting. They got lighting at night.
How does it convert light to energy? It's too complicated to talk about it.
Well, it does it with semiconductors, and it's a reaction between when it strikes the semiconductor, and the semiconductor absorbs that energy. We convert energy all the time. You know, we can't produce energy, but we can definitely do what? We can change its form. You know, that'd be saying, how do we take dams and convert it to electricity? Yeah, we let the water run, and it spins a turbine, and we use the spinning of a turbine to turn a generator. So what happens with semiconductors, and we see this even with the photo cells and the photo transistors, is they absorb that energy from the light, and it changes their characteristics. So here, the type of semiconductor that they use, and we can look it up and look at all the different methods, you know, all the different semiconductors they use, but there are some semiconductor materials that when light subtracts them, it takes that energy and converts it into a difference of electrical potential. And if we got a difference in electrical potential, then we can have what? We can have current flow. And then we can use that current to convert it over to DC. And of course, if you was in a camper, you know, you can go just about any place, any auto parts store, or maybe even Walmart, and buy 12-volt bulbs that's designed to run off of a battery, right? A standard car battery. Or you can buy what we call an inverter, and then the inverter take the output of the battery and convert it over to what? AC, you know, electronically.
No, I remember that.
Oh, guys, y'all get me off on tangents all the time. Well, it's me. I usually say, if it's not about the class, then don't ask a question. Because I get off on a tangent. So photovoltaic cells, that's a technical name. Photovoltaic cells. Most people call them what? Solar. If you want, by the way, and you do, so if I hook batteries in parallel, what do we increase? Yeah, so if I hook batteries in parallel, then what we do is we add the amps together. But you have to come over here and you have to hook them in the same direction. If you hook them in opposite directions, you have yeah, they're canceling themselves out, but they'll run down real fast because the other battery acts like a short circuit to the other battery. So the batteries will run down real fast. If I hook them in series, what do we change? Yeah, we change the voltage. And you see this all the time. Like on your remote, what advantage does a higher voltage have over a lower voltage? Less current to produce the power, to produce the required power, right? You understand? And usually a lower voltage would be cheaper. One battery would be cheaper than two batteries. But what you'll find out is there's very few things that just weren't off one. And these little things are not necessary. And this is a term that bothers me too, is that everybody calls these little C cells and these little D cells, they call them batteries, and they're not batteries. They're cells. And what we do is we hook cells in series to increase the voltage, and we hook them in parallel to increase the current. But people don't understand that. There's only one little old battery that you buy. That's that 9-volt battery. That is a battery. So if you took that thing and you tore it apart and cut it on, you'd see 6 cells inside there generating 9 volts, 1.5 volts per cell. But that's the commercial name for anything that chemically gives us a DC voltage. We call those things what? Batteries. Yeah, where's them cells at? Down at the Bessemer jail. That's the only place I know where they're cells.